Here comes another very popular projection method, and this is the so-called Galerkin method. There was no Mr. Collocation, but there is a Mr. Galerkin, and that's his photograph. So this is Boris Grigorievich Galerkin, an engineer and mathematician. Actually, if you want to get his name right, you should better write it in Cyrillic letters. And I think you can identify most of the letters, and the interesting one is this here. It's in Russian you call it yo, probably. So it's an E with two dots on top, and of course in the English alphabet you don't have that, or in the Latin alphabet you don't have that. So you just write E, and then you're tempted to call him Galerkin or Galerkin or something. But in fact you should say Galerkin, the yo. Okay, did I ever tell you I had to learn Russian at school? 8 painful years. Okay, long story, a long time ago. So let's get back to mathematics and Galerkin's method. We start with our operator A from x to y, where at least y needs a scalar product, and because we want approximation, we also appreciate completeness, so let y better be a Hilbert space. We will see while we're going what x needs to be, but well, we will see. And then you construct your finite dimensional subspaces xn and yn as the span of a linearly independent family of functions in x or respectively in y. And you better take the same number of functions here and here, because that makes the dimensions of your spaces xn and yn the same, and that's going to be important in what follows. So here is our setup. Okay, and now Hilbert space and orthogonality come in. You want the projection on this side that brings you down from y to yn to be the orthogonal projection. Whereas on the other side, let's assume we have any projection Pn from x onto xn. So one of the things that you do in projection methods is to take your right hand side B, which is of course typically not yet in the subspace yn, and you have to project it down to yn using that projection over here, and this is now the orthogonal projection. So in geometrical terms, this means that this difference vector here is orthogonal to this whole subspace yn here. Good, and now we are all excited to get to know the method of Boris Grigorievich Galerkin. Here we go. And you start as you always do, so you want to approximate the solution of your original equation, which is a unique solution because we are assuming A to be invertible. And we do that by approximations in our finite dimensional subspace xn. Okay, but now here's the important condition coming. And it says when you apply the operator A to your xn, and what you get project down to your subspace yn, then you get the best approximation of the desired right hand side B in the subspace yn. So let's try to see that here. So you want your little xn to be in the subspace capital Xn, and as always there is no reason why the image of little xn should be in yn, so it's typically outside. But if you project that down to yn using this orthogonal projection Pn hat, you arrive at that point in yn which is closest to B. And we all know by the approximation theorem which point that is. It's of course the point that you get when you apply your orthogonal projection to Bn. So it's the orthogonal projection of Bn down to Yn. This is the point that is closest to B inside of Yn. Okay, and that's going to be the same point where you arrive when you apply the orthogonal projection to Axn. That was Galerkin's idea. Okay, let's see how we can continue from that idea to a system, ideally an n by n linear equation that we can solve. Okay, as we just said, by the approximation theorem, we can explicitly write down that best approximation of B in Yn. And it's nothing but Pn hat of B. Now it's easy to rewrite that equation by getting everything to one side and factoring Pn hat out to the left. Okay, now let's play around a little bit with the projection Pn hat by just copying this equation over to here and squeezing one more Pn hat in here, which is of course redundant because Pn hat is a projection. Now keep in mind that Pn hat is the orthogonal projection onto subspace Yn. So if Pn hat maps something to 0, then that something is orthogonal to Yn. And of course we can make the same conclusion here. And maybe it helps to summarize everything in a little diagram. So let me draw the subspace Yn as a plane this time so we can see orthogonality a bit better. And the space surrounding that plane is our capital Y. And our right hand side B is here. And the best approximation of B in Yn, well, is obviously here. And when I say obviously, I mean this is mathematically underlined by the approximation theorem. So in particular to the green line connecting B and its projection, we have an orthogonality with the subspace Yn. And you can imagine your projector Pn hat like gravity, so it's just everything falls down to that subplane Yn. But of course, if you're underneath the plane, then gravity is dragging you up. Okay, and now over here in a completely different world, there's your space X and your subspace Xn, and your approximate solution little xn comes from Xn and is such that your operator A brings you over to that world here to a point that, if projected down to Yn, ends up at the very same point as B did when was being projected down to Yn, orthogonally using the orthogonal projection Pn hat. Okay, and now in that little diagram, I think we can recover all of our equations here. Well, the first one is that these 2 points coincide. The next one says that if you look at the difference of Axn and B, which is this long line here, you get a vector that if you project it down to Yn, you end up at 0, or in other words, that connection is orthogonal to our subspace and our image here, this plane Yn. Right, so connecting these 2 points gives you something that is orthogonal to Yn. Okay, so similarly, this statement down here is just saying that the connection between B and that point is orthogonal to Yn, and here we are expressing the same statement in terms of the projection, orthogonal projection Pn hat. You could probably come up with even further equivalent statements, but let's not lose focus here. I think we are ready now to write down, or to almost prepare the n by n system that we can solve in the end. So like before, we can rewrite our unknown because it's an element of that space xn as a linear combination of the basis elements b1 to bn of the subspace xn. And now the really unknowns, or the real unknowns now, are these real numbers alpha 1 to alpha n. And the other step comes here. So saying that a certain vector is orthogonal to the space yn is equivalent to saying that this very same vector is orthogonal to the basis elements of yn. Okay, should we recall notations quickly? Here we are. The space xn is spanned by b1 to bn, and the space yn is spanned by c1 to cn. And because both these families are linearly independent, they are each a basis of xn, respectively yn. Okay. Now this gives you n equations, and here are your n unknowns. So all that remains to do is to take this expansion here and to plug it into that statement, which ends up in n equations, and then you just have to do the maths. Let's do it together. So here we spell out xn as the linear combination that it is, and then, as we say here, a of this linear combination minus b is orthogonal to the vectors c1 up to cn. In fact, this is another equivalence sign here. Now, of course, you can again use linearity of a to get the summations out and the little alphas, and what you get is the following. So this term here splits into that one. Now let's rewrite that in terms of scalar products, and then use additivity of the scalar product in the first component, so you can split this up into two, or if you want even more scalar products. Then get the little alphas out here, and bring this term here to the other side. And then you have your system of n equations for the n unknowns alpha 1 up to alpha n. And it's a linear system, so let's rewrite it again in matrix vector form. And that's your n by n Galerkin system. Excellent. So let's take a deep breath and make a couple of comments. First comment is about that matrix here, which is of course the key part of this system. The computation of that n by n Galerkin matrix is generally numerically more expensive than the computation of the collocation matrix. And that is because computing the scalar products typically involves integrals, and that's a lot more expensive than just evaluating some functions, which is what you have to do when you compute the collocation matrix, right? So in both cases you have to apply your operator to the basis functions, but then here all you have to do is to evaluate the resulting function at some grid points, whereas in Galerkin you have to take that result of a applied to the basis function and put it in a scalar product with another basis function. A lot more expensive. But on the bright side, you get generally better convergence properties for the Galerkin method compared to the collocation method, essentially because Galerkin is working with these best approximations, and I mean, how can you beat that? Of course, in the end, you want to approximate x by the xn's, so you need something similar also on the x side, and that's when you want to choose your space x also a Hilbert space. So if you want to make sure you get very good convergence properties, then it's of benefit to also make x a Hilbert space and to also use orthogonal projections on that side. Second comment, how can we see Galerkin's method as a projection method? So we need our canonical form where A is squeezed between two projections. And I mean, we almost have it here. All we have to do is to just squeeze the projection Pn between A and Xn, where this projection Pn here is of course redundant because Xn is already in the subspace. There's no need to project it down again. Okay, but now you have the form that you want. So I think now everyone's convinced that Galerkin methods are projection methods.